This meeting will be recorded and shared in our YouTube channel. Hello, everyone. Welcome to the series of NERO Network Webinar Café. So today about an important concept in context of the fire behavior. Specifically, we will talk about the rate of spread. I believe that it's a crucial point when in context of the fire behavior, though this meeting it's important, I think, is the 50 webinar that we have in NERO. So I believe that this is a crucial point when we talk about the basic concepts of the fire behavior. So as you can see the title, we will see how we can apply the rate of spread, trying to give you different perspectives about the subject. So today we have the honor of hosting 3 experts. In this case, is from Australia. One of them is half Portuguese, half Australian. So we will start from scientific approach with Miguel Cruz, and after we will have David Phil trying to understand how we can apply this concept in the practice. In the end, we will have space to Q&A when you can ask questions about the theme. So Callan will moderate and try to give some dynamic this webinar. So I only give you the short perspective about the NERO project. So here you can see more about cost action NERO. Here in website, all the deliverables, opportunities, all the work that we are doing in NERO. You can join in the NERO network via our website. I invite you to view our website and our YouTube channel. So I forgot, but I'm Fabio Silva, and I'm leading the work group 3. So what NERO can offer you, it's important. So the NERO can offer funding for in-person and virtual exchange. So conference and some short-term scientific missions. We already have some opportunities in this year that exchange some experience with the practitioners and researchers into some organizations, into the real situations of the wildfire. So the focus of NERO is networking and try to improve the relationship between researchers and practitioners. Again, for more details and how we are developing this work, we can see in the website. Only for give you the overview perspective of the work plan of NERO. So you can see here that is divided in 4 work groups. In the work group 1, we are collecting data about the wildfires, mainly around Europe, but also we have some case studies outside of Europe. So work group 1 is collecting the data, mainly fire progressions, and the main goal is create the fire database that will be available for everyone. So in the end, everyone can use all this data. So the work group 2 will treat all this data and try to create knowledge with this kind of information. So not only we are collecting data, but also we have the goal to treat this data. So the work group 3 is about capacity building, and the work group 4 is about the communication. Into the work group 3, we have this webinar series. So the work group 3 is focused on capacity building. The main objectives of the work group 3 includes improvement and understand of the practitioners' needs, co-creation content and operational tools, and try to create knowledge and exchange experience mainly between the researchers and the practitioners. So as I said, the NERO Network Café is a webinar series, is an integral part of the activities within Workgroup 3. These webinars serve as a platform for dialogue, bringing together experts, practitioners, and researchers to discuss key issues. We are doing this monthly, so until now we are covering the basic concepts. I believe in the beginning of the next year we will have the more complex concepts, and so basically we are trying to develop this webinar. So today I'm co-leading this work group with Núria Prat from Focus Foundations, and now I will give the floor to our moderators, is Colin White, that joined us from Australia, is New South Wales Rural Fire Service, that is started in 2002, is recognized as one of the 7 area commanders and the only woman in this role. Have a lot of experience in context of the leadership, focusing on communities risk and engagement. So I believe that Calvin have the special skills in context of the communication, so is the right person to command our webinar. So I will stop to share my screen and I will give you the floor. Calvin, the command is yours. And thank you everyone again for joining us.
Thanks so much, Fabio. Really appreciate you asking me to be a part of this evening. So, and I should clarify, good evening from Australia and good morning to those of you that are on the webinar that are not in the evening. I'm Chief Superintendent Colin White. I'm a commander with the New South Wales Rural Fire Service. I've been with the agency for just rolling into my 23rd year for quite some time. It's an absolute pleasure to be moderating tonight's scientific and operational insights into rate of spread at the 5th NERO Network Café Webinar. We've got a couple of expert speakers this evening who are going to share groundbreaking research and really strong practical application of that research in wildfire behaviour management. So it's my pleasure to introduce Dr. McGill Cruz, who's the Principal Research Scientist, Bushfire Behaviour Modelling at the Commonwealth Scientific and Industrial Research Organisation, that is better known in Australia as the CSIRO. Dr. Cruz is a bushfire behaviour scientist with expertise in field experimentation, fire spread modelling, and he's got a strong emphasis in high intensity fire propagation, fire instrumentation design and assessment of effectiveness of vegetation modification to mitigate fire spread and intensity. I was speaking to David Field earlier today and he tells me that Dr. Cruz's motto is "You've got to burn to learn." So I'm really excited to hear his presentation. So Dr. Cruz is bringing 25 years of experience in bushfire behaviour research with an understanding and quantification of high intensity fires from Europe, North America and obviously Australia. McGill's work is focused on the development of new science with practical application and direct societal environmental benefits. And a number of his models are used operationally across Australia for both planning prescribed fire and forecasting wildfire. And the outputs of these models are used to inform warnings to communities and for safe and effective fire control and strategies. So Miguel, I'm super keen to learn about how you've got to burn to learn, and I'm excited to hear your presentation. So I'll pass over to you.
Thank you. Let me just no. Am I sharing my screen?
Yes.
I would like to start the presentation also by acknowledging my collaborator, Marty. We started working about 25 years ago, I believe. And Marty is a retired Canadian Forest Service researcher. He was one of the developers of the Canadian fire behavior prediction system, and also has a lot of work in terms of experimental work in crown fire propagation. In terms of fire rate of spread, it might seem a very simple concept. Some time ago, I was developing a guide for measuring described fire behavior in Australia. And after developing this guide, some people asked me, how do you measure rate of spread? So sometimes it's not very clear. So the rate of spread is defined as the speed a flame front advances across landscape, right? Is essentially the distance over time. And that graph on the left just shows experimental fire with the flame front location through time and showing d as a distance and the various time intervals. So it's a simple concept as we have a free spreading fire. Often, in terms of units, we tend to use, I personally like to use often meters per minute if we are working in low intensity fires. Meters per minute allow you to kind of visualize, if you are within the flame front or close to the flame front, visualize the propagation. It's quite handy, meters per minute. Whereas when you are predicting the propagation of wildfires, typically, and working with maps, large scales, you typically work with kilometers per hour. So in terms of the metric system, these two kind of units we typically use for the rate of fire spread. Now, what's the relevance of the rate of fire spread? And important to make a distinction between wildfires that are free spreading fires on the landscape and more confined industrial fires or urban fires, which typically tend to be confined with a certain area, right? Wildfires will spread as long as there's fuel available to consumption, as long as the fuel is dry, and as long as the wind is pushing the flame front. So as a wildfire is spreading the landscape, and you can show a few images there, namely the one on the right, Kilmore East Fire in Australia, 2009. You have there the perimeter of that fire. The final perimeter, and you have the active flame front from satellite. And you can imagine this fire spreading through the landscape. There's towns on the path of the wildfire. So there's a need to know when is this fire reaching different places on the landscape. So that's where the quite relevance of fire propagation. Often we also think about other key
Miguel, excuse me, can you hear me? Miguel.
Miguel, can you hear me? I think this is not good connection.
Yes, I'm afraid that he has some problems with connection. I sent him a message, but I'm not sure that he can see it. Does anybody have a way to contact him directly?
I will try. I'm Miguel.
Hello. Looks like for some reason my computer stopped.
Don't worry. Maybe it's I don't know if you have a good connection or not. We are seeing your presentation still. So
Okay.
we lose, yeah.
Let me share again because I don't see the window.
Okay. You can stop and start again because for my side I'm see your presentation.
Okay.
Okay. Now
Right.
you have the slide focus on rate of spread. Is this?
All right. So yeah. So just trying to so the importance of the rate of spread, and you go back to 50 years ago when even in the 50s. This is excerpt from Luke and MacArthur by Australia, and the goal of fire behavior research is to provide simple, timely answers to this kind of questions. It's about the fire rate of spread. From that, we can estimate the area, the perimeter of this wildfire, 2 3 hours, and so on. Also linked to the rate of fire spread, we have type of fire, the ground fire, surface fire, and also linked at intensity, which each type of fire is going to have spotting potential. I'm just not. Just a second. Yeah. So one important aspect to consider as well as we go into predicting fire behavior, predicting the rate of spread, is the concept that although typically when we aim to predict fire behavior, we tend to use average weather conditions, normally forecast on the hour. We might know fuels on the landscape, quite detailed or not. We might make crude assumptions, but fire behavior, so we tend to predict fire into what we call a steady state, a pseudo steady state. We are using fixed weather conditions, let's say average for the hour. But we know that fire propagation is quite variable through time, right? And that graph on the top there just illustrates that aspect, where we have fire for this Baideen fire early this year in Victoria, in Australia, and we have rate of spread as a function of time, and you see kind of goes up and down, peaks for a moment to about 12, 13 kilometers per hour, and then comes down again. So quite a dynamic variable. But when you try to predict, we tend to consider just more the pseudo state, steady state, kind of constant, as in equilibrium with the broad weather conditions. Another slide just to put into context where the rate of spread or prediction of rate of spread fits within the prediction of other variables or as a driver of other fire behavior. That flow chart on the right just shows, on the top we have the environmental factors, fuel bed characteristics, fuel complex, fuel moistures, wind speed, and slope. Those tend to determine firstly the rate of spread, or when we model fire behavior, that's how we look at it. And you're going to estimate other variables such as fire line intensity, and on the bottom there I have the equation for fire line intensity, where we have the heat content that tends to be fixed. If fuel consumed varies within a certain range, let's say between 5 tons per hectare to about 20 or 25 tons per hectare, and then the rate of spread. And rate of spread varies over orders of magnitude from, for example, 0.1 meter per minute to 100 meters per minute. So that is 4 orders of magnitude. So it's a variable that most vary within the fire environment, and has the most effect on variables such as the fire line intensity, which is the energy release rate from a fire, but others like flame characteristics, height, length, spotting distance, and things like that. So rate of spread is, I like to see it as the core of a lot of other fire behavior that we predict. So I guess there's often a general need to predict fire propagation, right? You want to know, let's say, you want to know your enemy, what's he going to do, right? You want to forecast that propagation. And there are different methods, some computer methods such as wildfire analyst or farsight, to name a few, well recognized internationally. There's the methods that were described by Richard Rothermel back in the 80s, that publication, How to Predict the Spread and Intensity of Forest and Range Fires. And just talking about the Australian case, we applied these methods, different software tools, but general methods as put forward by Rothermel. And that is applied, and I believe David will describe that, show some of examples. That is applied by personnel that are well trained on the models and well trained how to read the environment, and couple those things with their experience and predict fire behavior accurately, or accurately as possible, right? And myself and Marty have been developing models that are used by these fire behavior analysts through the several decades in Canada, in Australia, right? And a few years back, it came to a realization. We were investigating some of the Black Saturday fires, and we were interviewing people that were involved in the fires. And we're talking about the incident controller for one of the fires. And he was the first incident controller because it was the fire start in this fire brigade area. The fire was spreading quite fast and very quickly left his management area, probably crossed 2 other jurisdictional areas. But he was still the IC, and he was saying he had no clue where the fire was, right? And that just highlights the fact that although we have people trained to predict fire behavior with the models, different techniques, there will always be situations where, for us, there might not be qualified people to do that kind of calculations in a fire. Maybe because of the time of the day, maybe because of the location, or maybe because there's too many fires in the landscape and there's not enough of these fire behavior analysts to attend to all the fires. Or also sometimes there might not be enough time to conduct a detailed prediction of fire propagation, right? And so after years doing this kind of fire behavior modeling, more complex models, developing more complex models, come to the realization that we also need very simple tools, right, to predict fire behavior. And this concept of very simple tools goes back to this rule of thumb concept, where we talk about easily learned or easy applied procedures based on normally practical experience rather than theory. There's a few in fire. For example, some people talk about the 30-30-30 is a good example of a rule of thumb. It just tells you about the level of fire activity. In Canada, there's also the rule of thumb if relative humidity drops below air temperature, that is a signal that you're going to have some heightened fire activity. Just two examples that are used, right? No, normally these are very simple, and as said there, they're not intended to be very accurate or reliable in every situation. They have their niche where they are applicable. And this goes back, rule of thumbs, the concept of heuristics or mental shortcuts, things that people can get very quickly and make calculations of something that they need to know, right? And when you talk about this 10% rule of thumb for wildfire propagation, how this was developed, so this was not planned, right? It was something that just happened. Idea just happened from looking up other information. In this case, Francois Pimon is a researcher from INRA. He did some analysis of some data set that Marty and I put together of North American wildfires. And what Francois said is that for this data set of high intensity fires, so they're all crown fires in North American conifer forests, the ratio between the rate of spread and U10 is the open wind speed. You measure 10 meters, is the World Meteorological Organization standard, and normally weather forecasts use that wind metric. But when do the ratio between these two quantities, the average of the ratio was 0.09, right? And when we saw this value, we said, oh, this is interesting because this is very close to 0.1, which is 10%, right? And start thinking about, I wonder how this would work as a simple tool to predict fire propagation, right? Now, we didn't know how applicable that was, right? How representative would be this number, right? Namely, the variability around it. Is that high variability? It's almost like the average phone number of the phone book is meaningless, right? If there's a lot of variability. Or there's a situations where the ratio tends to this value, right? And how relevant is also this value be for other fuel types? This, again, the data set that Francois looked was conifer forests in North America. And we start thinking, okay, how relevant that result is for eucalypt forests or shrublands. I also put here a graph that was put forward by Kevin Tolhurst some years ago, more than 10 years ago, way before that publication. But what you see is that we have a ruler of the Forest Fire Danger Index, right? And you can see, if you look about Europe, could be the ISI, the Initial Spread Index. And then you have the effect of different fire environment components, right? So for low to moderate fire potential, fire danger index, fire will be fuel dominated, right? That's what the graph tries to show. As the fire danger increases, you start seeing fire is dominated by the fire itself, the interactions, or also topography driven, depends on the landscape, right? But as we go to very high, more to the extreme range of the fire danger index, what Kevin Tolhurst was prescribing is that then the fires become weather dominated. And this, because this extreme really is driven by the wind speed, then would be the fire being dominated by the wind speed, right? So we want to look at this ratio in between rate of spread and wind speed we go along that grading of fire danger. Okay. Oh. Okay. So for this analysis, what we did was we didn't have any data. Well, we didn't want to use any of our data. Wanted to use data that was already published in wildfire case studies, but they were published by others. We didn't want to pick and choose or use our data for that. So we went and put together 3 conifer forest data set that we published in 2006. And then there was a data set from Phil Cheney that published in 2012, and also another data set for shrublands. So Phil Cheney is a data set for eucalypt forests, and then a data set on shrublands published by Wendy Anderson, a researcher also in Australia, right? So this is kind of you see the number of fires in each data set for about almost 120 fires. Fire runs typically 1 to 3 hours. So again, talk about we're not capturing the fine variability of fire behavior, talking about broad time intervals. That's what we typically use in fire behavior prediction. And you also note that at this time, these data sets include some of the most notorious wildfires on record. So these were based on published case studies, high intensity fires that because of their relevance, they were studied and let's say quantified fire behavior and environmental conditions in a satisfactory way. Now, when you put all these data together, and the graph you see here is the rate of fire spread as a function of the open wind speed of all of the data in the data set, 3 different fuel types. One interesting aspect we see right away is that although the fuel types might be very different, right? We have conifer forests, a lot of fuel in the canopy, high intensity crown fires. We have eucalypt forests, a lot of spotting dynamics, not so much crown fire, but you have spotting is the dominant propagation mechanism, namely in these high intensity fires, and also shrubland fires. We talk about shrublands 2-4 meters, so a different dimension, different fuel types or fuel characteristics. Independent of that, when you make a regression of spread through the origin, the coefficients, the slope of this line tend to be very similar. So that was very interesting right away because despite the disparity in fuel characteristics that characterize these fuel complexes, it seemed that wind speed alone was explaining fire propagation in the same way, right? So that was encouraging. Now, a ratio of, if you use this overall ratio there, or slope 0.082, is not really a number that's amenable for a mental calculation. So we said, okay, instead of using that correction factor, let's use a 10%, 0.1, right? Because it's very easy to mentally divide the number by 10, right? And so we come up with this rule of thumb, where the rate of spread of a wildfire is given as 10% of the average open wind speed as measured 10 meters. So as an example, if the wind speed is 30 kilometers per hour, the rate of spread will be 3 kilometers per hour, right? And you obviously, you ask yourself, how is this possible? How is that possible that such a simple rule, it works, right? And of course, we're interested to know, does it work? How it works? In what situations does it work, right? And here, start looking at some of the data trends. Here we have the predicted rate of spread in the x-axis against the observed. We have the line of perfect agreement. That's where we like to have all the points. Of course, there's a lot of uncertainty, and namely when you talk about wildfire propagation, where weather data might be measured many kilometers away from the location of the fire. Even as the fire is spreading 10, 20, 30 kilometers in one day, as some of these fires did, you just realize that the fire might be moving away from a weather location that might be initially 20 kilometers from the point of ignition, right? Very dynamic environment. Now, here we have an area of under prediction. We don't like to have under prediction in fire spread models. There can be quite negative consequences. Over prediction, not as bad, but has its own bad consequences. Now, if you put here a line on the 2 km/h observed rate of spread, you kind of see that there's a lot of over prediction in this environment, right? There's a lot of fires spreading less than 2 km/h, and they're being over predicted by this rule of thumb. But when you go above this 2 km/h threshold, most of the fires are within this plus or minus 35% error band, right? And that's this error band we kind of determined some years ago from analysis of experimental data and also wildfire, which would be an acceptable prediction error, 35%, right? So that was encouraging that the fast fires, not all of them, but a very good number of them, were within this band. Okay, so let's look at some of the errors we're observing. Two plots show two of the errors that we normally use to quantify fire behavior prediction uncertainty. And we have this mean bias error and also have a mean absolute percent error, right? And on the x-axis, we have the fine depth fuel moisture content, right? So interesting that the higher errors is a bias, over prediction bias, so 0 will be no bias, right? So highest error is obtained for the higher fuel moistures, so milder conditions, right? And as you see here in this graph on the right, quite high fuel moistures, areas of 100, 150, but as we go low to the more typical severe wildfire conditions, the error tends to decrease. That's a very encouraging result, right? Because this is where the bad fires are going to occur. The fires that we need to really make predictions and warn the public of impending danger if that's going to occur. But for very low fuel moistures, it's time to observe the lowest errors, right? So that was interesting. And these are the error graphs here, look similarly, but on the x-axis, horizontal axis, we have the observed rate of fire spread, right? And again, what you see here is that mean bias error, you have over prediction for slower fire, for the slower fires, right? But as the fires increase, it goes close to 0, and then there's a larger under prediction bias, right? Now we need to consider also that although the bias tends to be larger, also the observed rate of spread is larger, right? So in terms of percent or relative error, what you observe is what's here on the right. So larger errors for slow spreading fires, right? But as the rate of spread increases, the error stays at about 40% in this data collection, right? And a good example is here. So for example, talk about between 5 and 6 observed rate of spread. You go up, you have an error under prediction. When the fire is spreading 5 to 6 km/h is less than 20%. So that's why you observe this decrease in rates of spread in the relative error on the right. So we then went and looked, let's try to characterize the error for the rule of thumb by conditions. And this kind of matrix tries to two groups of fuel moisture content, one higher than 7.5%, the other one lower than 7.5, right, the bottom. And then we have two wind speed groups, 0 to 30 and more than 30, right? And now let's look at the fire, at the errors. So for high moisture content, we have moderate winds and high winds. Errors of about 120 or 84%, so close to 100% error for these high moisture content situations. But when we go to the drier fuel conditions, we see that the errors really become smaller, right? So 54% for the moderate winds, but if you go to the high wind situation, 42%, right? And even here, you talk about the average rate of spread for this group of fires, 4.3 kilometers per hour. Mean bias was just a fraction of that, almost no bias for those kind of fires, right? So it looks like the rule of thumb is working well for the fires that matter, right? These are the fires that spread faster, that you are more likely to not have time for a detailed prediction of fire propagation. And that's where the rule of thumb is working best. We also did another comparison. We wanted to know, okay, how does this rule of thumb compare with the models that are used to predict fire propagation? And in this case, so we calculate the rate of spread using the most adequate models, ground fires for conifer forests. Eucalypt forest is the model for eucalypt forests in Australia, the Chineal 2012 model, and shrublands is a model developed by Wendy Anderson. And what we see here, again, the same kind of matrix as before, for high moisture contents, and you have moderate winds or high winds, we see the rule of thumb predicts errors much higher than the models, right, for these kind of conditions. So rule of thumb is the gray bars, and the black bars are the models. So this all the data together. And here we have the mean absolute error, MAE, then the bias, and the MAPE is the percent error, right? So, okay, for more moderate conditions, the models are predicting fire propagation much better. But when you go again to the low moisture contents, what you observe is that the models are not predicting much better than the rule of thumb itself, right? Errors, very, very similar, right? Fair enough, but one point needs to be made here is that in this situation, the rule of thumb is being evaluated against itself, the data that was used on its origin, where the models are being evaluated against independent data. So the rule of thumb for this graph has some advantage, right? So we then went and we wanted to do some further evaluation against fully independent of the data that was used for the development of the rule of thumb. And for this, we had two large data sets available. One was developed by Sarah Harris, currently with CFA, and Musa Killing for Australia, eucalypt forest, and you have about 180 wildfires in that. And the other data set was a data set compiled by Paulo Fernandes in Portugal through this bonfire project, and he looked at a lot of different sources to collect wildfire data. So when we go and do this evaluation of the rule of thumb, we already saying that the rule of thumb is only applicable for a set of conditions that are moisture content, find that fuel moisture content less than 7%, and winds more than 30 kilometers per hour. So we're already applying this threshold here. We're not interested in using the rule of thumb for other situations. We know it doesn't work very well. So we only want to focus on that kind of more high fire spread potential conditions. And then we put a few other filters. Drought factor, this is just an indicator. It will be like the BUI in the Canadian system. I believe most of you are aware of. It's used in Europe. Is a quantifier of the dryness of landscape. A 9 is pretty dry landscape in Australia. And then we have a run duration of more than an hour. Again, you don't want to use small time steps fire propagation. There's a lot of noise in those. We want to focus on the larger scale propagation, right? And so for the killing AL data set, so that from Musa and Sarah, so this just shows the results of this evaluation. In this case, again, we have the predictions for models, because these are all eucalypt forests. So we have also models used in Australia for eucalypt forests. That's the MacArthur and the Cheney. And again, if you look at the graph on the right, where we have the residuals as a function of observed rate of fire spread, you see the same feature as before. There's a number of fires that are spreading slower than 2 kilometers per hour that seem to be spreading slower than what you could expect. And they tend to be largely over-predicted. Whereas if you talk about the faster fires, more than 2 kilometers per hour, most of them within the plus or minus 35% error band, whereas the other models tend to have a mix of under prediction in this case. Yes, under prediction in this case, namely the MacArthur model, and then the more recent Cheney-Al model with some over prediction as well, kind of more balanced, but more fed off the results than the rule of thumb. So that was kind of interesting, because this again is independent data used for the evaluation. Then we're going to look into this bonfire. And again, for the bonfire, we had that in conifer forests, eucalypt forests, and shrublands. Again, we found the same trends, where we have fires, slow fires, less than 2 kilometers per hour, being over-predicted, whereas the other fires tend to be within the plus or minus predicted, within that plus or minus. You also observe there's a bit of a under prediction trend in this case, namely for a lot of these eucalypt fires. So if fires are going 8, 10, 12 kilometers per hour, what's happening normally, we have long range spotting for that kind of fire behavior, and the rule of thumb is not capture that. Still predicting within that close to that error band, but there's an under prediction bias for those very fast fires. So through that evaluation, again, we did some other analysis. This graph just shows, again, the percent error as an average for each of these kind of blocks of rates of spread, 2 kilometer intervals. And again, with error, and what you see is slow spreading fires being over predicted, largely errors of 200, 300%. But then for the fastest spread fires, the error is within that error margin. We figured out through that analysis that a threshold for application of the rule of thumb of 5% was better than the 7%. Again, with 7%, we might still have some over prediction of fire propagation. And then we start looking a bit on why are we over predicting these slow spreading fires, right? What's happening? We find out that some of them were early afternoon runs, whereas maybe the fuel moisture was being overestimated. Some of them, there was also suppression being effective in slowing the fire. And the other question was that we couldn't answer, but another possible reason is fire-atmosphere interactions. So what could happen is that for a lot of these fires that are being overpredicted is because strong convection blocking the effect, strong convection from the fire area blocking the effect of wind, and wind not being allowed to break into and push the fire forward as much as if the wind is stronger or if the convection was weaker. So this could be a possible reason also for this overprediction of slow spreading fires. So again, just summarizing a few of the major assumptions and limitations of this rule of thumb. Wind needs to be measured or forecast at the standard 10-meter height in the open. It's not the wind under the forest, is not the wind at 6 meters. Now, it's the forecasted 10-meter or measured 10-meter open wind speed. And it requires a homogeneously dry landscape. So again, midsummer, not early summer, where it's still dry. These drought factor landscapes can still be quite, in terms of fuel dryness, quite there's quite variation. Now it needs to be homogeneous dry, right? So midsummer, late summer fires is the target conditions. Again, works best when the fine dead fuel moisture content is quite low. Again, best when it's below 5%, 7% also acceptable, but not as good as below 5. And applicable for wildfires spreading in conifer forests, dry eucalypt forest, and shrub and fuel types, right? So this is the main fuel types that the rule is applicable. So there's a note there, not valid for grass fires. In fact, there's another work we conducted with wildfires from Australia that looks at a rule of thumb also for grass fires, and grass fires spread for the same wind speed spread about twice as fast as we were observing for these fuel types. So kind of the rule of thumb for grass fire is about 20%. Again, very similar analysis, not presented here, wildfire in grass fires, and similar results, but 20%. This is only applicable for large, longer than 1 hour wildfire runs. Even 1 hour is a bit of a shorter time step for some of these. You can, as I showed in that graph, Beidin fire, there's still a lot of fluctuation within an hour. If it's 2-3 hours, something like for an afternoon, that's where it kind of better averages that the variation in rates of spread that occurs in a wildfire. Is applicable fires on land level to gently undulating topography, or if the fire is of such size and it's just spreading across drainages with alternating upslope and downslope runs, right? So for that needs to be a fire that's so large that the fire is not responding to topography anymore, right? This fire is spotting across drainages, is making large runs upslope, might be slowing down, but slowing down in the downslope is overcome by spotting. So if it's a small run of a fire in a large slope, these would not be applicable. And also, the rule of thumb assumes that there are no appreciable barriers to fire growth. So again, homogeneously dry fuels, and if there are some breaks in the landscape, maybe different fuel types that are not as flammable, they cannot be of a size that would limit propagation, right? So anything that exists should be overcome by spotting. If not, the fire might stop or almost stop, whereas the rule is over predicting the propagation of the fire. Effect of spotting is implicit in the rule of thumb. The spotting was present in a lot of these data sets, so it's implicit there. But you need to account also that if you're talking about long range spotting, you talk about 10, 15 kilometers spotting, that's where we start to see some of those under predictions. In fact, some of those fires that were 10, 12 kilometers per hour, that were more under predicted by the rule, there was authenticated long range spot fires in those fires. So that's not, so we expect if that's going to occur, if there's the kind of winds that lead to that kind of propagation, long range spotting, and namely upper level winds, can expect that there's going to be some under prediction. And the last note in this limitation is that, again, there's a lot of uncertainty, namely in the data, in the wildfire propagation data, in the wildfire weather data. So using the rule of thumb, whenever any other model, expect an error interval of plus or minus 50%. So even if the model, the result is 3, you put 50% more, 4.5 to 3.5, for example. That's kind of the error band you could expect the rate of spread to be. Main applications, I guess, is when the time is of the essence, right? Is when there's little or no time available or no qualified person to undertake a detailed prediction of fire spread. That's where this can be used. Also, there's another aspect is to checking realism of more detailed predictions. And this is a bit complex aspect because it has to do with effect of other variables in the fire propagation. So if you think about that graph that shows that after certain conditions, the weather environment, namely wind speed, drives fire propagation, and the other variables have a minimal effect in a wildfire situation. When you think about this situation, we know that the fire behavior models, right, do not take that into account. The fire behavior models typically will have these multiplicative factors that are independent of the burning conditions. So sometimes we're going to apply models and the models are, let's say, on the edge or outside of the original data sets used in their development. You might start seeing the models kind of shooting kind of the prediction of fire behavior, going too large, for example, too high fire behavior prediction, because they're compounding these variables in places where the effect is not present. So the rule of thumb can aid into checking the realism of these predictions, right? So if the predictions using a model show that the value predicted is much higher than the rule of thumb, it might be the case where the model or combination of inputs are leading to results that exceed what can be expected. Again, while the rule of thumb is based on wildfire data, and a lot of the models we have only in Australia are not based on wildfire data. Right? So often we use outside. So this is my last slide, and not sure if there's any questions. I'll be happy to answer. All right, let me see the messages. Yeah, I can see chat. Okay. Hopefully it didn't break too much. Okay, first question I might answer here. Wind use is 10%, is the forecast wind or observed wind? I guess if you are aiming to predict fire behavior into the future, 3-4 hours, you will need to rely on the forecast wind, not the observed, although it might be the case where you check your observed wind with your forecast, and if you see large discrepancies, you might be tempted to make a judgment, adapt the forecast to meet what's observed, right? Because it might be a bias on the forecast. So normally use the forecast because you want to use into the future. Again, it depends on are the winds going to vary or not, are going to be constant throughout the day. If they are constant, maybe you could use the observed with the forecast wind. Again, it goes back to how your area is covered with automatic weather stations, right? How good are typically the weather forecasts for your area, right? And you need to make that judgment yourself, right?
Yeah. Let me suggest that.
Second question.
Let me suggest maybe you can answer in the end, because in this way we can promote the debate in the last the 30 minutes. So my suggestion is you answer in the last 30 minutes, if you agree, of course.
Sounds good.
Fantastic. Thanks so much, Miguel, for your presentation so far. And there are a few questions, so let's hold those. And I'd like to now introduce David Field, who's a fire behaviour analyst with the New South Wales Rural Fire Service. So David, or of course in Australia we give everyone a nickname, Fieldy, has been a fire behaviour analyst for the RFS over the last 10 years. And I've had the pleasure to work with David a number of times on some key projects. Over the last 10 years, he's worked on the most significant bush and grass fires that have occurred right across the state of New South Wales. He's also been deployed interstate and also internationally. David's been establishing the RFS's upper air weather observation capability, and he has been supporting national research projects, which have kept him really busy, along with providing information and research to support criminal and coronial investigations, and has then worked on the delivery of a large number of those inquiry and Royal Commission recommendations. David's really passionate about using his research to help improve firefighting and organisational decision making. So, Fieldy, I'll hand over to you.
Thanks very much, Kelvin. Yeah, just to give people a quick flavour of what the Rural Fire Service is in Australia and in our state of New South Wales. We're one of the 8 states and territories in Australia. And in a typical year, the Rural Fire Service will respond to around a couple of thousand wildfires, basically. And I guess in a really busy year, that could be up to about 10,000 different fire incidents that we're responding to. We're mainly a volunteer fire agency, so we have around 70,000 volunteer firefighters, and all of our frontline personnel essentially are volunteers. So they do the firefighting work for the government free of charge, basically. I'm a fire behaviour analyst, and I've seen a few people in the chat that look like they have a similar role in different countries. So I'll just share my screen now. And I guess hopefully that's coming through for people. I just wanted to present, I guess, like maybe a firefighter or a practitioner's perspective of the work that Miguel and his colleagues have done. So on the 10% rule of thumb. And I'll just start with a slide that is kind of similar to how Miguel ended up there, basically, which I think that, you know, the 10% rule of thumb is certainly something that's incredibly useful for people who are out in the field, or firefighters who are wildland firefighters, or we'd call them in Australia bush firefighters. And I guess that falls into Miguel's category of when time is of the essence. And so these people are often, you know, dealing with radio communications. They might be dealing with members of the public. They're trying their very best to immediately have some kind of suppression activity and effect on putting out a fire. And so their time for calculating how fast a fire is likely to spread, or even what a fire is likely to look like, is pretty minimal. And so that's one of the reasons that I think the 10% rule of thumb for forest firefighting is really useful in Australia. It's simple, it's quick, easy to use, and it helps those people who are, I guess, at the most risk from the fire to quickly appraise what that fire's potential is. One of the other things that's really useful from their perspective as well is the fact that the 10% rule of thumb gives them an idea of how fast the fire is likely to spread into the future. If you followed what Miguel was saying about using the forecast wind speeds, they can use that information if they're a divisional commander in the field to look at which parts of the landscape are likely to be threatened in the future, and they can provide that intelligence back into command centres to hopefully get more support through additional resources and things like that. This is the sort of sphere that I typically work in, which you'd probably call the strategic sphere or the command sphere of firefighting, and this is our office in Sydney, Australia. And I think the 10% rule is very useful in this context as well. And Miguel referred to it as like checking the realism of a more detailed fire spread prediction. And I think it's got a lot of use in this sphere in terms of being able to very quickly identify like a combination of weather conditions and fuel moisture conditions that are able to drive a very significant fire run. And so that helps even at an arm's length or for people that are, I guess, not necessarily face to face with the fire. That helps them build confidence that the conditions are bad enough that perhaps the intelligence that's coming back from the field about how quickly that fire is spreading or how aggressively that fire is spreading is accurate and legitimate. So that's kind of that real checking realism that Miguel was talking about right at the end of his presentation. So I guess just to show you how I would think about the 10% rule and how we sort of might look to use it in Australia and in New South Wales, I thought I'd step you through a bit of an example of one of the fires that we had, not this fire season, but the fire season a year ago. So this example is about the Coagulite Road fire, and a good example of some of the things that Miguel was talking about in terms of the inputs that go into the 10% rule as a fire spread model. So the story for this fire begins 4 years before that fire actually spread. And so the story for this fire begins in Black Summer, which you probably would have seen on the news, which occurred in the 2019 and 2020 fire season in Australia. And it's widely documented as the worst fire season that we had, at least in New South Wales. Unfortunately, 26 people lost their lives. We lost 2,746 homes and close to or above 5.5 million hectares of land burnt. And I guess the reason why we've rolled back to this point in time is that a lot of the fire that occurred in Black Summer was very intense fire. It was a drought-stricken landscape, and so the fires were burning over very extended periods, and so they really burnt quite severely and reduced the fuel loads quite intensely. So flash forward now to our example, which is in the previous year just gone for us. So it's about a year ago now, but it was in the 2023-2024 fire season for us. And this is 4 years after the Black Summer fires. A new fire starts, which is the Coagulite Road fire, and it starts in an area that was burnt during Black Summer. So you can see in that map there, those black shapes in this map are the areas that were burnt during Black Summer, and at this time 4 years ago. And we've had a new fire start in this area. So why is this significant? Well, basically, if the area is burnt within 4 years, we would commonly expect the fuel loads in that area to be very low. We would also expect the continuity of that fuel that is relatively sparse to also be quite low. And the combination of these factors would kind of lead us to suggest that, or to, I guess, assume that the forest that had been burnt is probably unlikely to be able to support a fast running fire. And so in this case, what we have is an area that's been burned. It has very low fuels, but it is an area that would normally have quite productive fuels. So the forest is recovering in this area, but it's still early in its recovery, and we don't really expect it to be able to carry, I guess, a fast running fire. So there's a bit of, I guess, uncertainty initially as we're trying to appraise the potential of this fire or assess the potential of this fire. And that's where we move into, I guess, the weather conditions. And so the weather conditions for this fire were where we had essentially a fairly drought-stricken landscape. So as Miguel was talking about, you need a uniformly dry landscape for the 10% rule of thumb to be kind of in its range. And Miguel mentioned drought factor there, which is fuel availability and it needing to be above 9. So we have that in this instance. In fact, we have 9.8, which is almost as dry as it can be, if you like. We also have fairly strong wind speeds. So we have wind speeds, average wind speeds of around 30 to 40 kilometers an hour. So they're above the sort of 30 kilometer an hour threshold that the 10% rule of thumb needs. And we also have a modeled fine fuel moisture content of around 5%. So that's definitely less than the 7.5%. And it's also in range of, I guess, that really skillful part of the 10% rule of thumb. That suggests it's skillful around the sort of 5% rule. So here we've essentially met the threshold conditions for the 10% rule of thumb, which basically suggests to us that the kind of, I guess, influence that the fuel is likely to have on this fire is starting to become less influential on how that fire would actually behave. For us, this is a very challenging situation because we would typically expect an area that had been burnt quite recently to really, I guess, suppress or make the fire behavior in that area a lot more benign. But as you can see from this photo that was taken in the afternoon of the 3rd of October 2023, the Calagalite fire was able to take hold very quickly and spread very aggressively. So here, this is a little bit hard to understand this map, but this is the black outline is the eventual final extent of the Calagalite Road fire, measured from, I guess, the top left-hand corner of the map to the bottom right-hand corner of the map. The fire is spread around 14 to 16 kilometers in a period of around 5 hours. The sort of strange coloured image that you can see overlaid with the map is the Black Summer fire scar. And this is what we call our fire severity and extent mapping project data, and that's basically derived from satellite, and that shows that in the red that there's a fair bit of like high severity fire, and there's a fair chunk of that fire scar in the Calagalite Road fire's path as it tries to spread down to the sort of right hand side of the map. So we can see there that if you just take those figures of the 14 to 16 kilometers an hour in a period of around 5 hours, you're looking at a rate of spread of around 2.8 to 3.2 kilometers an hour. And if you go back to the wind speeds that were being experienced on this fire of around 30 to 40 k's an hour, you can see that the 10% rule of thumb provides like a fairly accurate depiction of the potential of this fire. In terms of its ability to spread rapidly through the landscape. Especially in this instance, it's quite interesting that, I guess the fact that the area was already burnt is a confusing factor for us. And so having things like the 10% rule of thumb helps us clarify that, this behavior is likely to occur, despite perhaps our preconceived notions about areas that have been burnt recently. And that's a bit of an image of what the forest would have looked like at that point in time. So whilst that might look pretty productive for that part of the world, normally that part of the world has such dense forests that you could kind of barely see through it. So that is actually like a relatively sparse I guess, example of that kind of forest. And you can see the burn scars on the trees from the Black Summer fires there. So I guess to sort of, further expand on that point, here is 2 simulators that we ran this fire in, or tried to model or simulate this fire in. And the one on the left is using Vesta Mark II, which is a fire spread model that Miguel Cruz was also instrumental in creating for us. And the one on the right uses is called Phoenix, but is predominantly based on MacArthur Mark V, which is another Australian dry eucalypt fire spread model. MacArthur Mark V heavily leverages the amount of fuel in terms of tons per hectare to determine the rate of spread. And so what you can see in these two maps is the same fire has been run in two different models and two different simulators. And in the one that's, I guess, more focused on what the effect of the fuel will be, it's pulled up the fire at the edge of the Black Summer fire scar and is suggesting to us that the fire is unlikely to spread through that fire scar. Whereas Vesta Mark II, which has sort of, I guess, some components of the 10% rule of thumb built into it, understands that the threshold conditions have been met, and at this sort of like extreme of weather, fuel is unlikely to play as much of a significant role. And so in that simulation, the fire spreads like through that burn scar and down towards the community that you can see on the coast there. These are just a couple of other predictions that were produced at the time, and they use some updated intelligence about the location of the fire. And one of those is a hand-drawn, hand-calculated prediction, which you can see on the right-hand side, and then the other one is an updated spark prediction. The reason that I'm showing you these is because I guess, this sort of shows that things like the 10% rule of thumb, this is an image of those predictions overlaid against a medium wave infrared scan of the fire at 7 p.m. Are able to produce a fairly accurate account for how that fire would spread through the landscape in a particularly challenging situation where there is uncertainty about what role the fuel will play. And so I suppose that's kind of all I have for our presentation, but hopefully that gives you a bit of a good flavour of the operational use that I see for things like the 10% rule, and it really is in those ideas that Miguel spoke about, where it's good for being used in the field when time is of the essence, and it's even good when you're in a command centre and you're trying to check the realism of some kind of simulation that you've just prepared as well. So thank you very much.
Thanks so much, Dave. Really appreciate your operational insights there. And thank you to Miguel as well. I think that was really thought-provoking, giving us the insight into the science behind the rate of spread and wind speed as that dominant factor in wildfire spread and what we see routinely in Australia. There is a couple of questions in the chat. So Miguel, for you, when you use observations of wind data, how representative are these of the conditions at the actual fire site?
I guess, but let me be clear. I'm not I don't make simulations in the field. I'm not a F-man. But I guess, again, it depends on the situation. Depends, different areas will have different representativeness of the weather data, right? You might have areas with a lot of weather stations with very good wind data, representative of the area of the simulation, or we might have situations where there's no weather stations, or there's a weather station that is in a really bad place. So we know that wind is not representative of the fire itself. So again, it goes back to looking at the landscape, look at the sources, how representative this wind can be or not. I'll typically tend to use more the forecast if I'm in a situation like that. But I always check the forecast with the existing wind and check the realism of the weather forecast for the present conditions. And from there, move forward. That said, I think fire weather forecasts tend to be very, very good in Australia. Just there's a lot of need. The people that do that kind of work are very knowledgeable of the needs and knowledge of the landscape and what needs to be done to do this accurate predictions. Again, a lot of times when you have these kind of events, there's a person, a weather forecaster, that's assigned to a fire. So the role of this person is to produce the best weather forecast possible. So it's not just a machine output without being verified by a person.
Yeah, I can also expand on that if you like, Miguel and Cohen. So our process in New South Wales would be to verify the forecast, like Miguel was saying. So check whether the forecast is verifying well against the observed weather. And if that's not the case, so the forecast weather is not verifying well against the observed weather, we would then request a meteorologist change or edit the forecast for us, so that we have a more accurate forecast to be using for our simulations. So the seat that I sit in at work has a meteorologist from our federal meteorological agency sitting next to me. So to give you an idea of how closely we work.
And I might also
Thanks, David.
if I might compliment Dylan, in the question from Domingos, it might also be related to the wildfire data we used, right? And if that's related to the wildfire data we used, we didn't have much control on that, right? A lot of that data was historical data, at times with not so many weather stations. So the data has a lot of noise in itself. So that's also explaining some of that variability we see in the graphs.
Thanks, Miguel. I see our friend Fabio has asked a question there in the chat as well. So Miguel, for you, Fabio's asking, it could be interesting to characterize the types of convective smoke columns that limit the practical application of the 10% rule of thumb. And he's saying this because of the graph that determines the environmental conditions, determine the rate of spread of the most critical events. So do you have any thoughts on that?
Yeah, yes, certainly. I guess the next step is always trying to apply, understand the limitations, understand what's happening in future fires, document what's happening, if it's working, it's not working, what visual guides can we extract from a situation. Again, the images that David showed really showed this kind of really well bent plume. It looks like a big cigar on the landscape, right? That's also a result of not much fuel, so there's not much energy being released by the fire, not much buoyancy, but another indicator of very strong winds. So that's where the rule situations. Yeah, it's certainly markers from the plume might be indicative of when the rule will work or not. We haven't done any work on that again, but it's certainly a place to look.
David, could you explain how technically in Australia, and obviously in your role in the New South Wales Rural Fire Service, how fire behaviour analysts determine and predict the rate of spread? So are you using simulators, manual predictions, observations? What goes into it?
Yeah, sure. I guess the main thing an analyst in Australia is going to be using is their own calculations of rate of spread from a fire spread model. So Miguel talked a little bit about those, and they're a little bit more detailed than the 10% rule in that they'll take in maybe a wider range of fuel conditions, and they might have a bit more skill in different ranges of like how a fire might behave. So we have sort of calculators for those, like a range of different calculators that we can put in weather variables, fuel variables, and then we can consult a range of different fire spread models to look at what the rates of spread for that fire will be, or those kind of conditions will be. What what we tend to do in New South Wales is we basically try to use consensus modelling as much as we can. So we do have a couple of simulators that I showed in my presentation called Spark, CSIRO Spark, and also Phoenix, as well as that sort of manual calculated hand-drawn process that I also showed in my presentation. And what we'll try to do for the worst of our fires is try to simulate them in all three different ways and look to see how much they agree with each other. And if they agree with each other a lot, that gives us good confidence that that's likely to occur. Or if there's discrepancies between them, we can then cross-examine each piece of information to work out why there's differences between them. So we sort of use that almost like a poor person's ensemble method to try and either build consensus or identify, you know, issues that have sort of crept into the process, if you like. Hopefully that answers that question.
Question in the chat here. So the rule of thumb is quite good to apply in wind fire topology. How do you in Australia, when you have different types of fire behaviour, either topographic or convective, how do you apply it?
Do you want me to go, Miguel? You're the expert.
No, you are the expert.
I just work with the tools you give me, good sir. So one of the other things that the fire scientists like Miguel have developed for us in Australia is, I guess, an understanding of what how the rate of spread would accelerate or decelerate, either accelerating upslope as the fire spreads upslope, and also decelerate as the fire is likely to spread downslope. So we have those kinds of calculations that we can do by hand, and they're also built into some of our simulators. One of the important things to kind of point out as part of that process is to have a think about how the fire is actually propagating or moving through the landscape. So in Australia, we have a lot of eucalypt trees that have a lot of flammable bark that gets torn off and thrown ahead of the fire. And that leads to that kind of spotting behavior that we get for our fires. And so we have seen situations where even though the fire is trying to propagate downslope, which would normally slow the fire down, spotting basically assists the fire to propagate down that slope relatively quickly. So it's also important to not just, I guess, take into account the effective slope on its own. You need to also have a think about, like, necessarily how the fire is going to spread through the landscape.
Thanks, Dave. Another question for you, and you've been quoted in this one. So Joanna has said, first of all, thanks for a great presentation and moderation to all the speakers. One question from my side: how well would you say does the poor man's ensemble technique work for you in general? Does it accurately enough predict fire behaviour, or do you feel better models are required?
I think like any kind of modeling application, you could always have some kind of improvement to the tools, for sure. But I think that technique is not probably utilized as often as it should be. So if you have multiple methods for predicting some kind of fire wherever you are in the landscape, I think it's a good method to basically try and use every available method and then see how much sort of similarity and correlation there is between them. Miguel showed in his presentation that a lot of even good fire spread models have a range of uncertainty of potentially plus or minus 35%. And that's not talking about necessarily the uncertainty that's already exists with things like a weather forecast and things like that as well. And so there's a lot of uncertainty that goes into the process. So the more that you can do to try and, I guess, build certainty through the process seems to be really useful. We've done it for probably a decade now. And yeah, we find it very useful, I suppose.
Great, thank you. There's no more questions in the chat, but I'm sure there are some burning questions out there. So if anyone would like to ask Miguel or David a question, please raise your hand. We've got another one now. Is there any rule or threshold regarding live fuel moisture?
not really explicitly. Now, when we have a drought factor or fuel availability close to 10, everything is very dry. So the shrubs, the trees, all these kind of fuels are close to being hydraulically stressed. So they are kind of close to their minimal moisture contents, let's say, that they can allow to continue living. So although it's not explicitly included in the model, it's implicit in there, right? Because when you talk about the fuel availability, in the Australian context, we talk about this drought factor goes up to a value of 10. And for example, available, large twigs become available to combustion. Live vegetation becomes available to combustion. So it's everything. So it's not just the fine fuels, it's all the other fuels that are going to start being available to combustion. So it's very difficult to empirically extract the effect of the live fuel moisture from the other dead fuel moisture, like coarser fuels, dead fuels, right? So that's why it's very difficult for us to explicitly quantify that effect, but it's, yes, implicit in the model.
Thanks, Miguel. We've had a comment from Marco, who's written here, looking backwards, there are some Portuguese case studies, pure wildfire behaviour. The rule of thumb applies perfectly, not in the 10 metres, but to win at 950. Do you have any thoughts or comments on that, Miguel or David?
I'll leave it for David.
Thanks, Miguel. Look, it sounds like there's some kind of like fire atmosphere interaction going on if you're finding that the winds aloft are more closely aligned to how the fire is behaving. I know we've had a few situations in New South Wales in the last 5 years where we've had nocturnal inversions eroded and nocturnal jets kind of recruited down to the surface. And so that would be a situation where your sort of 10-meter wind forecast doesn't have a lot of skill predicting the wind that is actually affecting the fire, because the fire is kind of changing the environment and entraining some of those stronger winds aloft. We don't necessarily see it in deep mixed layers like in a typical summer day for us too much. It's more in those sort of strange overnight fire spreads that we kind of see that behavior. But yeah, it sounds like there's some kind of fire atmosphere interaction occurring there potentially.
David, I was just thinking back to your slides, and you had the picture obviously of the truck en route to the fire there, and you're talking about the 10% rule for application of firefighters in the field, that it's very simple and quick to assess the potential fire behaviour and rapidly identify what is potentially going to be threatened, or for that initial situational report. Do you have any thoughts on using this as more in the sense of when we're in that first chaos of a fire and we're trying to get intelligence from the ground, and perhaps the application in a public safety sense in terms of, I guess something I would have done is for public messaging and warnings. Do you have anything there to add?
Yeah, I think that's the real strength of the 10% rule, is its sort of simplicity and ease of use. And so it's really accessible to the crews that are time poor. It's accessible potentially to members of the public as well, like so that, and I really think that for me as an FBAN, it's that sort of checking the realism aspect. And I think that's also useful to even members of the public and firefighters too, because often, you know, at least in Australia, there's a long drive sometimes to get to where the fire is, and they might know some information about what the weather conditions are going to be when they get there. They might hear reports that the fire might be, you know, behaving intensely, and I guess if they're able to also check check the realism of those reports as well. It helps them build a mental picture of what they're responding to and what they're going to be dealing with when they arrive. And for members of the public, it helps them understand, I guess, the danger that is associated with a particular combination of weather conditions on a particular day too. Yeah.
That's a really interesting application thought, because when I started to ask you that question, I was thinking more from a public information officer's point of view. In if we weren't able to get quick intelligence and situation reports from the field, we could look at, you know, the conditions and quickly make assumptions to get those warning messages out. And then in the way that you've just answered that question, I'm thinking back to initially when fire danger ratings were developed. They were obviously developed for rates of, for the ability to suppress fire. But we've seen, particularly in Australia, that's become a tool that's really used for community engagement and education. So you think that potentially there could be the same application of the rule of thumb as a way for the community to understand and make decisions as well?
Yeah, absolutely. I would really like to see, you know, a version of the 10% rule built into the Australian fire danger rating system. And one of the things that, you know, we've sort of tried to cover off in a high level of detail is Miguel has not only developed the 10% rule of thumb, but he's also built a lot of that core knowledge into one of our more detailed fire spread models as well, which is the Vesta Mark II fire spread model. So being able to incorporate that into fire danger, yes, would be a very good idea, I think, for the public's perspective. Yep.
Miguel, is there anything that you came to say this evening that you've not mentioned yet?
No, not really. But although your last conversation really raised the issue, and thinking about past events and this issue that we might have people doing simulations. The information passes to through the chain of command or information until is released to the public, right? Often you might have very good predictions, but that does not mean that you're going to have timely warnings. So again, as you were talking here, have the people that are, for example, responsible for the warnings have also this kind of understanding. So maybe they can take that role before they are told by somebody in the incident management team, right? Because maybe there's a break in communication in the incident management team, right? And you see that over and over in fires that cause multiple fatalities throughout the world. The public was not warned, but maybe some people knew what knew what was going to happen, but was just had no way to pass that message, right? So the warnings are just not about the fire behavior prediction, is much more about how we have that information and provide those timely warnings. So again, it's maybe another role for the rule of thumb in that sense. Just
Yeah,
because it's simple.
I think you're quite correct there, Miguel, and particularly, I guess, from the experience of the 2019-2020 Black Summer fires here in Australia. I spent a lot of time working in the public information units, both in our state operations in Sydney and also at local incident management teams. And because of the severity and impact of those fires, and you know, as a community, we've become so reliant on technology, and we saw, you know, vast areas, communication systems just completely being taken out. I definitely can see it as a different application for that operational decision making, whether it's for firefighters, incident management teams, or potentially even the community. We've got a couple of more questions. So in plume-driven fires, do you think it could be a good idea to assess the speed of updrafts and adjust wind speed increased by the updraft? Sounds like a good one for you, David.
No worries. I get all the cool fire atmosphere interaction questions. I think Miguel kind of covered this a little bit when he was sort of saying that the fires that are spreading under 2 kilometers an hour, often what's happening is the sort of I guess the buoyancy of like the amount of updraft that's coming out of the fire is kind of, I guess, creating too much turbulence for that sort of 20-kilometer-hour winds, if you like, to kind of push through the forest and then affect the mid flame height. And so I think rather than probably necessarily adjust the winds, like what we would typically do in Australia is step back to a fire spread model that kind of understands that relationship between the sort of lower wind speeds, the buoyancy of the fire's plume, and even the frictional drag that's occurring as the wind tries to push through the forest and affect the flame that's within the forest. And so, yeah, I think for that question, we'd be using a different fire spread model that kind of understands that combination of factors, I suppose. Yeah.
Thank you. And one more question for you, Miguel. With regards to the estimation of the rule of thumb, during the presentation you talked about, you checked for some causes and identified some potential issues. Do you think that the rule can be applied anyway, as long as the fire does not fall into those conditions?
Well, the issue will be that, so the overestimation when the fire spreads in less than 2 kilometers is after the fact observation, right? So it is, yeah, so I don't think there's an easy answer for that. Again, David is know-how
You broke up
on
there.
these application situations where the rule didn't work. I guess the issue is that we are at a risk that the rule is going to overpredict the propagation, right? That's the risk. Again, early afternoon fires, we saw that was a cause, but there's other early afternoon fires that were well within the bounds of the model expectations. So there's no answer. It's like more data is required to kind of look into those aspects, essentially.
Yeah, I think you probably need a slightly more complex model at that point to try and resolve those conditions. Is that fair to say? Because you're getting wind interacting with the forest and things like that, potentially, Miguel?
Yes, and things like the issue with fuel moisture is known as a limitation of our fire behavior prediction methods. We know that if we have, for example, moisture recovery overnight, substantial moisture recovery overnight, the model doesn't take that into account. So the model will going to say that the fuel's already dry, but they might not be dry because the models are quite wet in the morning. So might be only later in the day that the moistures are going to be on the threshold, but we think they are already in the early afternoon. So that's a possible reason. So that's because of the inadequacies of our modeling. The other aspects, namely that is it the plume that's holding the fire? And it was mentioned earlier, looking to maybe you're looking at the cases where it doesn't work. What's the plume doing? Is that plume quite straight for the winds? So that kind of might shed some information on that. I guess we just need more data to better understand what's going on.
Thanks so much, Miguel. Fieldy, was there anything else that you came to say this evening that you've not had a chance to mention?
No, nothing from me. Thanks, Gal.
That's great. Well, thank you, Miguel. Thank you, David. And I'm going to hand back to Fabio to close off for the evening.
Okay. So thank you very much again for your participation. So I know it's almost 10 p.m. maybe, and in your home. So yeah, it was amazing. I think this kind of the information, this kind of concept is crucial to in order we understand better the fire behaviors. So we will try to bring other kind of concepts. And to December, we will have other meetings. So as soon as possible, we will publish that. So thank you everybody to join us, and I expect it so you like it so much as I like it. So I again thank you very much, Miguel. Thank you very much, David and Calvin, for your participation, and we will come back in December. So nice to see you. Bye bye.
Thank you. Bye.
Thanks very much, everyone. Thanks, Kelvin.
Thanks
Good to
all.
see you, David.
Good to see you, mate. Take care.
Thanks, David. Thanks, Miguel.